Exploring Earth's Interior with 3D Wave Simulations, Part 2. Hi, I'm Neala Creasy. I'm a postdoc at Colorado School of Mines, and I will be presenting some forward 3D wave simulations and also just some examples of travel time sensitivity kernels. So this is kind of an extension of the last talk that was posted on YouTube on Ebru's talk on forward and inverse problem of looking at global Earth structure, calculating sensitivity kernels, looking at tomography, and some of the computational costs that are involved with this process. So in the outline of this talk, I will be showing a walkthrough on synthetic simulations and some travel time sensitivity kernels. I will also briefly mention the forward modeling of SKS and also S and SCS, but also be discussing a little bit about looking at shear wave splitting as well, looking at the modeling of it from a ray theoretical perspective and also from a finite frequency perspective. And then also looking at how the mantle and crust can actually significantly affect the waveforms of these phases, such as the SKS, which we're really interested in this work. And then I will just do a brief walkthrough on the process of calculating a body wave sensitivity travel time kernel through forward simulations, adjoint sources, and adjoint simulations. And then I'll just show some examples of sensitivity kernels. So like the one I'm showing here is just an example of what they look like again. Okay, so the goals of this work are really just to how mantle anisotropy and or heterogeneity, like isotropic heterogeneity, affects outer core modeling. And also just as a tangential goal is to do the eventual global inversion of anisotropy with shear wave splitting. And then another tangential goal too is ray theory always appropriate in modeling shear wave splitting? I'm just showing an example from a 2016 Nowacki and Wiki paper where they looked at finite frequency effects. So on SCS, which is the wave, it's a shear wave that starts at the source and then bounces off the core. And they compared ray theoretical modeling of different elastic tensor models. I won't go into the details of this. Just the emphasis here is how sometimes ray theory can actually significantly differ from finite frequency predictions of shear wave splitting. So these are fast directions of shear wave splitting using particular elastic tensors for different kinds of SCS data sets. And so they showed that their actually finite frequency can have a really strong effect on predicted shear wave splitting parameters that sometimes ray theory can be limited on. And they really showed that that occurs when you have a lot of heterogeneity, which is something that we're interested in. Okay, so just to kind of also review Maureen's talk on shear wave splitting, just a reminder that this is an SKS wave here. I'm just showing an example of SKS splitting. That if we have no anisotropy, there should be a linear particle motion. And when I say particle motion, I mean it's where you plot the horizontal components against each other. So this is north-south and east-west. You can also plot the radial versus transverse component. If there was no anisotropy or no apparent anisotropy, then this particle motion should be completely linear. But in this case, there is anisotropy beneath the station. In this example, because we have energy on the transverse component. And this is very important of what the shape looks like, is that it should be an ellipse. This elliptical motion is important because the slow arrival or the transverse component should be akin to the time derivative of the fast arrival, and that's always going to have this elliptical pattern. And so that's something important to consider. If it has some other shape, it's likely not anisotropy, and this is just based on theory. Okay, so that's just a review of that. And then I will also just briefly cover ray theory versus finite frequency modeling. Ebru did a great introduction of what ray theory is and how it differs from finite frequency theory. And I'm sure Ed Garnero will recognize this figure. There's also, when we want to consider finite frequency, it's a great tool because we can model any phase and not worry about these ray theoretical predictions. The finite frequency modeling or the forward modeling will take everything into account. It'll take into account other phases that are coming in at the same time. we'll consider other phases such as these SPDKS phases. They are these little diffracting phases. Ed knows more about this than I do, but they do show up in waveforms sometimes, especially around these regions known as ULVZs, ultra low velocity zones. I won't go into the details of that, but just a reminder that ray theory is, of course, an infinite high frequency approximation, and finite frequencies considers that a wave is made up of finite frequencies. And what's great about 3D wave simulations is you can take that all into account, and you can focus on particular frequency bands. Okay. So just a reminder of how we even do ray theoretical modeling of shear wave splitting is it's all based on the elastic tensor. And the elastic tensor is just a way to describe, how a material compresses pretty much. And this is just the general elastic tensor has 21 components such as this. And from a ray theoretical perspective, if we want to predict the predicted shear wave splitting parameters, we use what is known as the Crustal equation. And it's important to understand the assumptions behind how we, predict ray theory, like predict these fast directions and delay times. And the main assumption behind it is that you have to assume a plane wave approximation. So if you take this form of the wave equation and you take a plane wave and you insert into the wave equation, you end up with this equation here, and this is known as the Crustal equation. And it's just a way to break down the elastic tensor and solve for your different, polarization directions of your incoming wave. So you have your P wave, and then you have your two shear waves. You have the SV, and the SH coming in, and they can come in at different velocities, and that's of course the anisotropy. So I'm just showing an example of what the isotropic solution is to the Crustal equation. So this is the isotropic elastic tensor, and lambda and mu are the Lemay parameters. And just a reminder, to get to VP and VS shear velocities, we mainly use the bulk modulus and shear modulus, and this is just a reminder of what that equation is. And ultimately, we end up with a solution here. So this is T. That's this equation over here. And T is the elastic tensor times these different polarization vectors. And so they pretty much they identify for you this is the VP component, this is the VSV and VSH. And you can insert this into this equation and solve for velocity. And if you want more information on this actual derivation of the Crustal equation, I refer you to Main Price 1990 and then the Walker and Wookie 2012 paper. So this is pretty much how ray theoretical modeling works for a given elastic tensor when we compare it to real data. And so if this is at all confusing, I'm happy to discuss more at the end of the video. Okay, so what's really cool though is you don't have to worry about coding up any of these equations. There's already great toolkit out there that some of you already know about. It's MSAT, it's a MATLAB toolkit. And with this approach, it's super easy and really fast to calculate ray theoretical predictions of shear wave splitting with any elastic tensor. You can input any elastic tensor you want. And this was written by the University of Bristol, University of Leeds team in the UK. And here's a link here. It's very easy to find. And with this toolkit, you can actually do a lot of visualization, such as this, where you can take any elastic tensor and visualize the shear wave splitting predictions given different azimuths and inclinations of a particular ray. So when I showed the Crustal equation, that's for one particular orientation of the elastic tensor. But a reminder of what a tensor is, it's a matrix with direction. So you can rotate the tensor in any direction that you want. And that's pretty much what's showing here is what the predicted shear wave splitting predictions should be for different azimuths and different inclinations of your ray. And so that's where the ray theoretical modeling also comes back into play is, you have to know the inclination and azimuth of that ray. And just assuming the infinite frequency approximation. So this is a great toolkit. There's a lot of things you can do in it. And if you don't have MATLAB, there are openly available Fortran codes as well that from the Main Price 1990 paper that you can use instead if you don't have MATLAB, because I know not everyone has it. So that's the only issue with this code, is that you have to have a MATLAB license to use it, unfortunately. Okay. And so just to kind of get back to the ray theoretical modeling of shear wave splitting. So when you measure these fast directions and delay times, this again is that same plot from before. This is just a visualization of what I'm showing here. And these little black sticks are the fast directions. So that's the fast direction from the Crustal equation solution. And then the strength or the color of this 3D representation is the strength of anisotropy. So that's the difference between the fast component and the slow. And that's going to be a function, your delay time is going to be a function of that strength as well. So that's how we relate to real measurements, is the delay time is the offset in time between the fast and slow components of SKS at your station. And then the incoming fast polarization is related to these little black sticks that are shown here. And so this is just, and then, so then you can input also your inclination here of your ray through whatever layer that you're interested in, and then, the azimuth of that ray as well. And so this is just an example of just how someone may model this with ray theory, is you can insert, maybe a hexagonal HTI, geometry. So with a shear plane and a shear direction, you can model that in MSAT, and then produce predicted splitting and compare them to real data. So these are solutions that they found with their particular data set from this study between, a particular elastic tensor model. Okay. And so when we come back to the body waves that we're interested in for mantle anisotropy, these are really the main ones that we're interested in, which is S and SCS for anisotropy, because they kind of graze along the core mantle boundary. They come at a very low angle. And then of course, all the KSs, all the PKS, SKS, SKKS, and even S diffracted has also been used to some extent for looking at anisotropy in the deep mantle. So of course, SKS, as we all know really well, it starts as a shear wave and then is a P wave in the outer core, and then a shear wave as it exits. But PKS is also heavily used in shear wave splitting, but instead, of course, it just starts as a P wave at the source, and then also P wave in the outer core. And I'm just showing here, this is just a map of all the regional body wave anisotropy studies that have been done near the core mantle boundary, just as an example. And most of these studies have used some combination of these phases, or multiple, pretty much. Okay. So, so if we want to use forward simulations to kind of simulate predicted splitting, all we have to do is just run the forward simulation, and you just input any elastic tensor model that you're interested in. And so one thing that I've started with in my research is just looking at isotropic background models. And if there are any anomalous splits that are occurring, that's just due to heterogeneity or crustal effects or finite frequency effects. So, there's no anisotropy. If there's no anisotropy, then whatever you're seeing is due to, these anomalous effects. So that's something that we can look forward to in forward simulations, is there anomalous splitting in isotropic forward waveform modeling. And that's something that I want to explore in my own research, is can finite frequency effects look like splitting? Do they look like the time derivative of the radial component? There's many studies that have explored this, and but oftentimes they only compare the fast and slow component and their offset in time, but they don't actually look at the waveform shape. And so that's really important to take into account, because like an experienced shear wave splitter would look at a waveform and be like, that doesn't look like the time derivative. That's probably not a reliable measurement. And so that's why it's important to constrain these differences. And so I'm just going to show some forward simulations of how turning on different knobs in the forward simulations can actually affect the overall waveform. So I'm just showing here some synthetic seismograms from Spectrum 3D Globe. Again, there's no anisotropy. And this, as you can see, that I'm showing SKS waveforms on the transverse component. You see no energy, which is what we expect. It's beautiful. There's no apparent anisotropy from mantle or from finite frequency. And this goes down to 9 seconds, which should cover the main frequencies that are present in SKS. And so this is for a shallow event in the mid-Atlantic at 12 kilometers depth. And I'm just showing synthetics for PREM, which are in black, and then synthetics for GLAD M15, which Ebru talked about, her model that, that she produced, and that's a 3D full waveform inversion model. And you can see that there are significant differences in the waveforms just by adding 3D mantle heterogeneity. And you can even see that in S diffracted over here as well. And so that's something that it would be interesting to also add anisotropy into this to see, okay, well, do we get consistent splitting between, you know, an isotropic background model versus a 3D? So this is, it's pretty exciting to also use these same differences in these same four models to look at the outer core, how it affects outer core model corrections as well. And so we can also compare different 3D background models. So I'm showing 3 different background models here, S20RTS, S40RTS, and GLAD M15. I will show on the next slide the tomography images and how they differ. But for now, I'm just showing you the waveforms for SKS, as well as, you know, SKKS as well. And this is the same event. And overall, you know, these three different tomography models are quite different. S20RTS and S40RTS are not based on full waveform inversion, so their approaches are very different. And they use, I believe, mainly travel times, but they use, you know, surface waves, they use body waves, they use normal modes. And so as you can see, they are similar in many cases, but there are some examples where they are very different from each other. S20RTS and S40RTS are fairly similar to each other. So as you can see, there aren't too many differences between, you know, these two models in green and magenta. But when we compare it to GLAD M15, we do find some scenarios where they can be significantly different. And I'll show more examples of that. But yeah, so overall, even different tomography models can produce different results. And overall, that one of the reasons for that too, I'm just showing an example of these different tomography models at 2,600 kilometers in depth. Here's S40RTS, S20RTS, and then GLAD M15. And as you can see, GLAD M15 predicts much stronger travel time anomalies for this Pacific large low shear velocity province. This is much stronger than in S40RTS. So you're going to get larger delay times, you know, in those arrivals of phases that go through this region. So that's ultimately one of the reasons why you're going to have differences. And so another thing that you can also look at is crustal effects. So here I am showing when you consider a 3D crust versus a 1D crust. So in this simulation, I did also S20RTS, you know, this is the same event, same waveforms, but in one of the simulations, I did a 1D crust where you average over PREM versus a 3D crust, which here I specifically used crust 2.0. The next slide, I will describe more specifically what crust 2.0 is, but it's a 3D model of the crust. And as you can see here, there are significant differences, but when you use a 1D crust versus a 3D crust. And actually, I would almost say that it has a larger effect than mantle heterogeneity. There are significant waveform differences in the overall SKS pattern. Even when, you know, looking at, these are stations mainly on the continents, I'll show some further examples that the ocean can also, you know, create some oceanic crust can also create some very large differences as well. And so that's something that's really interesting and something to explore also in the outer core modeling is different crustal models as well. And there are more crustal models than just crust 2.0. So, and I'm also going to show the transverse component here too of the same waveforms. There's even differences in S diffracted as well that are quite significant and that changes the overall shape of the waveform. And so here is just what the 3D crust kind of looks like. I'm showing crust 1.0, which is not too different from crust 2.0. Crust 2.0 is what I used. It's a 2 by 2 degree grid of 3D crust, and then crust 1.0 is just a little finer in resolution. It's 1 by 1, and it has MOHO depths in the model as well as velocity structure as well. So that's pretty much what the 3D crust looks like. And you can visualize these on Iris EMC. It's a great resource to have. Okay. So, but also, so I was just showing shallow events, but there's also significant differences when you look at deep events, because often, you know, we think deep events are cleaner for seismologists, but actually there can be really significant differences in the waveforms between 1D background models and 3D as well. Just showing an example here between S20 RTS Prem and GLADM 15. And this is at 570 kilometers depth in South America. So even deep events can produce such significant differences. I will say the differences aren't as severe as shallow events. They seem to produce more differences, but even deep events can. Okay, so, but I'm going to briefly show some S and SCS waveforms as well. I will even say that when you look at different phases, the differences between the waveforms are even more significant, especially for S and SCS waveforms. This is a 200-kilometer event near New Zealand. And as you can see, these are waves propagating through the Pacific Large Low Shear Velocity province. And there are significant, travel time offsets, between GLADM 15 and S20 RTS in green. And that's, again, I mentioned that before, GLADM 15 predicts much stronger differences in slower velocities through this large low shear velocity province. And there's also even significant differences in their waveform shapes as well. And I'll just remind people that in Ebru's talk, if the waveform shapes are different, your kernels are going to look different too. And so that's going to be an interesting thing to explore as well. Because if your waveform shapes look very similar, their kernels are going to be pretty similar as well. And what's really interesting about S and SCS as well is that you get very different striking waveforms even between 1D and 3D models as well. So this will be interesting to explore with the effects on shear splitting too that I mentioned. So there's a lot of really interesting things to explore with just looking at just different background models and things like that. Okay, so I'm going to show another example also on SCS and how the crust can also affect the waveforms. This is an example of the same mid-Atlantic event over here. And here's the transverse component and radial component of S and SCS. And there are some significant differences when you just look at, this is looking at a 3D crust. This is crust 2.0 over here. So this is in green is S20 RTS, red is GLADM 15, and then Prem. And there are significant waveform differences between 1D and 3D. And these differences mainly come from the crust, because if you model S20 RTS with a 1D crust, this is shown in blue, those differences kind of disappear. So crustal effects also have a huge effect on, this is SP here. And SP or PS, they start off as a P wave and then they bounce on the surface and then come back down. So the 3D crust really affects these waveforms and their shapes as well. And ultimately, what's really striking from this too is that these PS and SP arrivals are very, very strong, and they would significantly affect if you try to make shear wave splitting measurements on S waves or SCS waves as well. So this is also something that you can explore too, is other incoming phases and how much they would affect these phases that are of particular interest for shear wave splitting. So I know S and SCS are not really relevant for the outer core modeling, but it's relevant for modeling mantle anisotropy. Okay, so now I'm going to switch gears here. I'm going to switch gears over to travel time sensitivity kernels a little bit and just show examples. These are popcorn kernels. They're not actual kernels I'll be discussing. So when talking about finite frequency kernels, in these cases, I'm showing kernels that don't use real seismic data, and that's totally fine. You can do that, and they provide a lot of really useful information. So you're calculating the sensitivity kernels on synthetic data, and they provide great information about where the sensitivity is of a particular parameter if you're looking at travel times or amplitude or anisotropy. And so they're really great for looking at that. So the overall steps to calculating sensitivity kernels is, the first step is to conduct a forward wave simulation. And it's important with this, when calculating the forward wave simulation, you have to save the final step. You save all the files for that so that when you do the adjoint simulation, you can use those to backpropagate. And then the second step is to calculate the adjoint source. And Ebru talked a lot about that. She is the expert on calculating adjoint sources. And that's going to be dependent on your misfit functions. So there's a lot of choices in this step. And then you calculate your adjoint wave field. And that's when we go the backward in time. And Ebru did a good job of explaining that. And then the last step is visualization. So plotting the kernel, choosing what parameters you're interested in. When you calculate sensitivity kernels, they calculate kernels for pretty much every parameter. They calculate them for every component of the 21 elastic tensor and density as well. So it calculates everything. So you just pick the ones that you're interested in. So in this case, the main ones that we're typically interested in is density, VP, velocity, and VS. And so basically these kernels are built from the different kernels for shear modulus and bulk modulus. So that's pretty much how they're formed. So you can take the different, that's pretty much how anisotropic kernels are also calculated too, is you just take the different components of the elastic tensor and you construct the kernel from those parameters. So that's really nice. So you don't have to recalculate, your kernel simulations. You have all the data there for you. Okay, so for this forward simulation part, which I'll talk briefly about, the computational side of this. So it's pretty necessary to use parallel computing. Just if you want to go down to the resolution that we're interested in, which is probably around 9 seconds, you have to use parallel computing, so CPUs or GPUs. And so how InspectVim works is that you have the globe and it's broken up into 6 chunks. And each chunk will be broken up into further chunks. And each processor of the parallel computing will handle, that one little piece. So that's just an example here. What this picture shows is that there's a different processor on each of these little pieces inside the globe. And so if you want to get at resolution, you have to design your mesh. And so 256 elements along the side of one chunk is approximately, will give you 17-second seismograms. But if we want to go down to 9 seconds, we need 480 elements along one side of the chunk. And so this is just the general equation of InspectVim. This is the number of elements here. And so you can calculate what period that you're interested in. You can calculate the number of elements that you need in your simulation. So this is a really useful equation. And so then the next step is you have to pick your number of processors. And this will depend on the number of processors you have available and the memory constraints as well. So of course, as you add more elements, you need more memory and you need more processors because maybe one processor can only handle 5 gigabytes. And so you have to handle that as well. A whole mesh can be tens of gigabytes. So you have to have enough processors to handle all that memory. And so this is just an example of different resolutions and different number of processors you can have for different resolutions. So of course, the more processors you have, it'll be faster. But you have to have access to all those processors as well. But then I will reiterate that for adjoint simulations, you have to save the final time step if you want to do that. But this is just the approach for the forward simulations. Now, computational costs are really interesting too. Because there's even like a science behind like the number of processors you should choose for your simulations. And I will say that HPC time, high performance computing time, is pretty much required to do these simulations. I do all my simulations on XSeed right now or on Windian, which is the Colorado School of Mines cluster. But there are also other high performance clusters as well, like Frontera that I know Ebru uses. And so this is just an example of how to kind of determine computational costs. They're called scaling tests. And there's something called strong scaling and weak scaling. And this is on one particular system. This will vary between different systems. This is on Comet. It's the old system at the San Diego High Performance Computing Center. And you can look at how, as you increase the number of processors for the same resolution and how the speed up time increases. And it should be linear. And there's an ideal speed up that it should follow. But in reality, speed up doesn't always follow the ideal line. So these are for different resolutions. So this is NEX 160. Again, NEX is the number of elements along one chunk. So this is pretty low resolution. Here's 256 and then 480, which is the one I'm interested in. And you can actually see for 256, as you go up to around 1500 processors, the speed up does not follow ideal anymore. And that's just because it's becoming more inefficient as you add more processors. And weak scaling is just another way to determine computational efficiency, where you keep the same amount of work, but you increase number of processors, and it should follow the ideal line as well. And this can vary on different systems. This is just comparing to bridges. On bridges, 256 is actually scales really well, ideally, for all of them, versus this one, which falls off the line. So it'll vary on different systems, and weak scaling is actually quite different too. So this is important to know for each of systems, because you want to be as efficient as possible in the number of processors you're using. It's like, yes, you could use 1500 processors and it will be faster, but at some point you're going to lose gains on that and it's not going to be any faster. And so I use Expanse mainly for the simulations I've shown here and the ones that I'm showing now. Expanse is the new high performance computing center that's replaced Comet at San Diego. And I'm just going to show some computational times on Expanse. This will vary. I just want to give a sense for people like how long these simulations take. And these will vary significantly from system to system. So don't take this as the holy grail or anything. But Expanse does have amazing scaling. It's already better than Comet from before. And I will say a 9-second simulation that I've already shown on, I've been using 864 processors. A 130-minute seismogram takes about 3 hours for one event. So that's quite a long time. But compared to 17 seconds on 384 processors, it takes 48 minutes. So it's quite exponential, the amount of time you need, the more resolution you go up. So it's really difficult to go beyond 9 seconds. You have to have significant high performance computing allocation times. But yeah, so if you're ever interested in high performance computing, XC is great to apply for. Okay, so so after calculating your forward simulations, you have to calculate your adjoint source. I'm just gonna briefly touch on this, from Ebru's talk. She described it in length. I'm just showing the example for travel time sensitivity kernels. This is just the misfit function for, between your observed and synthetic travel times. But what's nice is in synthetic data, you don't need this because these are just scalar values. What you're really interested in is the part of the adjoint source that really controls the shape of the kernel, which is the derivative of the waveform. So I'm just showing an example of an SKS wave and its adjoint source, and it looks like it's derivative. So I'm just showing an example of that. And so there's many different adjoint sources you can calculate. This is just one example, a commonly used one, let's say. And then you calculate, you do your adjoint simulation. So you go backwards in time. And I'm just kind of skipping over that step 2 because Ebru talked about that in length, did a really good job. And I'm just showing the results from a paper, which I forgot the citation for this, but this is, I will correct that in the YouTube comments. But this is a pure SH wave example in 2 dimensions. So as you can see, if you look at the shear modulus, this is the kernel. And if you look at the bulk, so if you look at the VS kernel, this is here. And so that's constructed from mu, shear modulus, and density, which is the equation of shear velocity. And so then ultimately you have this. And so of course, for a pure SH wave, you should have no bulk modulus sensitivity and no P wave sensitivity. So if you plotted all the parameters, this is pretty much what you get. But pretty much in papers, when you read them or presentations, you'll see the final result, and it's a combination of these equations. Okay, just to kind of give you an idea about that. So I'm just showing some kernels, travel time sensitivity kernels that I've calculated at 17 seconds. I'm currently working on going up to 9 seconds. We're just completing the forward simulation part. But these are just 17-second simulations that they are much faster to run. So, we did them as a test to start out. These are the chosen SKS and SKKS waves, that I picked for this particular example. And this is for kernels for PREM, which is shown in orange, and S20RTS in blue. And then this is the particular array path that I use, this S20RTS model. And then here are the travel time sensitivity kernels for SKS and SKKS for PREM, and then S20RTS. So what I'm showing here is that this is the VS travel time sensitivity kernel and the Mantle, because it's an S wave. And then for the outer core, it's P waves. So I'm plotting here the P wave sensitivity, so the VP sensitivity. If I plotted the S wave sensitivity, it would be blank. There would be nothing there. So it's not very relevant. And overall, there aren't too many differences here. And like I said before, it's because their waveforms are very similar in shape. But as I've shown already, that I think they're pretty similar because they're at 17 seconds. But as I showed in my example, at 9 seconds, they're very different in waveform. So this will be really interesting to do at the higher resolution, but just to show an example. And so in these travel time sensitivity kernels, of course, their widths are very wide, and that's because we're at 17 seconds. If we go to 9 seconds, they will be tighter in their width as well. Yeah, and so in SKKS, you can see the beautiful bounce point on the underside of the outer core. And so these will also be great to do these same travel time sensitivity kernels for S and KS phases, such as S3KS and so forth. And that should be definitely possible. I didn't show any examples, but I do see beautiful S and KS phases in the synthetics. They do beautifully show up, so they shouldn't be a problem. And so here's for S and SCS. Again, don't see too many differences. I'm just showing S20RTS, and then I'm also showing an example from Liu and Trump 2008. They did S and SCS travel time sensitivity kernels as well for different frequency bands. So you can really see, as you go down in frequency, you see that thinning of the Fresnel zone here. And when I do it for S20RTS, they're quite similar as well. This is for a different distance, but hopefully, when I go down to 9 seconds, we'll see some more interesting variations. And then, so PKS is also an interesting phase. I'm unaware of any other PKS travel time sensitivity kernels. I don't think they've been calculated before, till now maybe. So this is for, again, 17 seconds kernel. And so PKS, again, starts as a P wave. So when we look at the S wave sensitivity kernel, there really is no kernel here because it starts as a P wave, and this is the S velocity. But we see, a nice kernel over here for the S part of the PKS. And then here is the P wave sensitivity in the outer core. And it's quite complicated because with PKS, there's also a triplication. We have 3 different phases arriving at the same time. So it's kind of complicated. And this is the beauty of finite frequency modeling, is that it doesn't matter if there are other phases coming in. You can still analyze the waveform and even analyze it for Shear splitting too down the line. So it's quite interesting. And though, again, their waveforms are pretty similar. So, there aren't too many differences between these kernels. Between PREM and S20RTS, there aren't too many differences. So just as an example, I will say what's interesting, though, is if we compare to SKS, the SKS width of the kernel is much thinner than PKS. PKS is much wider in its sensitivity. And that's just because of these other phases that are coming in at the same time. So it's interesting, PKS splitting is often used alongside SKS splitting. So it'll be interesting to explore, well, sometimes there are differences between the Shear splitting, and this could be because their sensitivity kernels are a little bit different from each other. And then I also just show you the alpha kernel for PKS as well, because you can see the nice PKS, the P part of the PKS as well. So I just wanted to show that for your edification, that we are seeing PKS here. So it's kind of cool. Okay. And so now last one is S diffracted. S diffracted, again, you don't see that many differences, but this is that phase that diffracts along the outer core. And yeah, it's pretty similar between the two, and it's beautiful. Yeah, so hopefully at 9 seconds, we can see some more differences. But yeah, there aren't too many differences with this phase, but this phase is really useful in looking at anisotropy because it has such a long ray path along the core mantle boundary. And so, of course, there have been other kernels that have been calculated in other papers. I will just say, but I think there could be more exploration, such as phases that haven't been looked at, like SKKS and PKS. I think this is the first time calculating those. And so, this paper, Liu and Trump did a whole kernel gallery. I highly recommend checking it out. It's a great paper. And they have P waves, P diffracted, PKP, little sp, little ss, pp, ss, beautiful kernels that could be useful for many people. Okay, so yeah, in conclusion, I find it crucial to calculate these travel time kernels, especially for the outer core model studies. You can really see where your travel time sensitivity kernels are for your SKKS phases. And so the important note is that your kernels will be different if your waveforms look different, because ultimately the adjoint source will look different as well. And so that will result in a different solution. It's also, in general, important to characterize a mantle heterogeneity and its effects on measurements, modeling kernels and such, just because it hasn't really been explored yet. So, and there are already, I showed that there are significant mantle heterogeneity effects on waveforms, and as well as huge crustal effects. And just a reminder, if you're interested in the Insight Toolkit, it's a great toolkit to visualize anisotropy. But yeah, that's really all I have. I mean, I do have to acknowledge XSEED in all of my talks, so I acknowledge them.